So predicting shapes of molecules. We've learned how to write Lewis structures, and we're going to use the Lewis structures to predict the shapes of molecules. The shape of a molecule is very important because it determines many of its physical and chemical properties. So the theory we're going to use for this is called valence shell electron pair repulsion theory, or VSEPR for short. And we tend to pronounce that VESPR, even though the E and the S get mixed up in there. So valence shell electron pair repulsion. So we're talking about valence shell electrons, pairs of those electrons repelling each other. And this is the idea behind this, that the electron groups are going to repel each other. Now it's important to understand, what are we calling an electron group? Okay, one electron group would be a lone pair of electrons, that's one group. A single bond is one group. A double bond is one group of electrons, and a triple bond is one group. My 6 children are one herd of children, right? They belong to the same family. They can't separate from each other. So they are one group. The repulsion between those negative charges on the central atom determines the geometry of the molecule. So if we look at carbon dioxide, here's the Lewis structure for carbon dioxide. We are going to look at the central atom. We're going to stick with small molecules and just look at the central atom. So on the central atom, we have a double bond over here and a double bond over here. That's 2 electron groups. And you think about, well, how can those 2 groups get away from each other? Well, they're going to be on opposite sides of the carbon. So I think of this as, maybe this is you and this is your ex, who just turned out to be really, really evil, right? And you hate them so much. You're going to live on opposite sides of the planet. And that's as far away as you can get from that person, right? Opposite sides. So if this is planet Earth, you're on one side, your ex is on the other side of the planet. So this is 2 things getting away from each other. So this oxygen atom is going to be on the opposite side of the carbon from the other oxygen atom. And so then we see that these are going to be in a line, and the angle of this bond with that bond is 180 degrees. And so this is a linear geometry. Any questions? H2CO, we did this Lewis structure earlier. So here's the Lewis structure. Look at the central atom. How many electron groups, not pairs, groups? There's a single bond, a double bond, and a single bond. Each of those is a group. So 3 groups. So now you have 3 things trying to get away from each other. So these can get away from each other in a plane by separating 120 degrees. So the 3 groups will make this shape. This is called trigonal planar geometry. It's a triangle, and it's in a plane. It's flat. Okay, trigonal planar. If we look at CH4, I made the model of it over there. So here's the carbon, and it has 4 single bonds. Each bond is a group. So 4 groups. 4 groups get away from each other by moving into a 3-dimensional shape, a tetrahedron. The tetrahedron takes the angles of a sphere and divides them equally, and you end up with angles of 109.5. So this one, trigonal planar, has angles of 120. And this one has 4 equal angles in 3-dimensional space. So a tetrahedron, geometric shape that has 4 triangular faces, not square planar. This looks flat, right? This would have angles of 90 degrees. But these groups are trying to get away from each other. And by popping into a 3-dimensional shape, they can increase the angle from 90 to 109.5. Which, if you're trying to get away from somebody, just that extra little space can mean a lot. Just talk to two siblings sitting in the back seat. You're touching me, you're breathing on me, right? Just a little, just an inch of space between is much better, right? So let's look at ammonia. So here's the Lewis structure for ammonia. And again, we're going to look at the central atom and ask ourselves, well, how many electron groups? Well, we have 3 single bonds and a lone pair. The lone pair counts as a group. So 3 single bonds and a lone pair, 4 electron groups. 4 electron groups make a tetrahedron. So it's going to make this tetrahedral shape with 3 hydrogen atoms in 3 of the corners and a lone pair in the 4th corner. So we call this the electron geometry. That's the arrangement of the electron groups. The electron geometry is tetrahedral. But the actual shape of the molecule is a trigonal pyramid. That's why we don't use it for the other one. So this is a trigonal pyramid. This lone pair is important. It's repulsive, and it's actually more repulsive than the single bonds. The single bonds dislike the lone pair more than they dislike each other. So they're willing to squeeze a little bit closer to each other to avoid that lone pair. So in terms of the balloons, yeah, that pink one has a hole in it. Of course it does. Well, let's not look at the balloons. Let's look at my model. So this is what the electron groups do. And when you have a lone pair, just imagine making that one invisible. Okay, I took the atom off. There's no atom there. And when we talk about a molecular geometry, we're looking at just where the atoms are. We have to look at the electron geometry first, because that lone pair causes these 3 hydrogen atoms to be pushed down. This is not trigonal planar, it's a trigonal pyramid because it's lifted up in the middle. You see that? So we look at the electrons first, the electron groups. Then if there's lone pairs, just make them invisible. So that's a trigonal pyramid. Let's look at water, H2O. Here's the Lewis structure. Central atom, we've got 2 lone pairs, two bonding pairs, 2 single bonds. So again, a total of 4 electron groups. 4 electron groups make a tetrahedron. Question?
Those lone pairs only count when they're on the center.
We're only looking at things on the central atom. Yeah, only things on the central atom. So tetrahedron, so it's going to make this shape here. But now 2 of those corners are lone pairs. So we're just making those invisible. And in fact, I can do that. So we just say, oh, well, the lone pair, it's still there, but it's invisible. It's like Wonder Woman's airplane. Right, that's invisible, and this is invisible. They are there, but you can't see them, which kind of makes sense because electrons are super small, right? And so what we've got left is given the very fancy name, bent. Okay? So if I took my original methane molecule and took 2 of the hydrogen atoms off, that's the shape. It's sort of like a V shape. It's called bent. Okay? So here's a table from your book, which I think is helpful, but don't rely on it to answer all the questions that you might, all the problems you need to solve. So here, if you have 2 electron groups, you're going to have 2 bonding groups and no lone pairs. Your electron geometry is linear. Your molecular geometry is linear. And here's an example. Yes?
I didn't really understand what you meant by ignore the lone pairs.
Well, you're not ignoring them really. You're pretending they're invisible, that you can't see them.
But on NH3, that would change the shape to trigonal pyramidal. Like, why they're not the same?
Well, water, let's go back to that. So there are there are two single bonds to atoms, and there are two lone pairs. The two lone pairs we pretend are invisible, and what's left is these two atoms. And so that's called bent. It can't be trigonal planar.
Is that because there are two lone pairs and not just one?
Yeah, this is going to be bent instead of trigonal pyramid because there's two lone pairs instead of just one. So there's two things that are invisible instead of just one. If you have 3 electron groups, the possible things that can happen here, you can have 3 bonding groups and no lone pairs, or you can have 2 bonding groups and 1 lone pair. The electron geometry is the same, trigonal planar. And so some students, look at this table and you're like, yeesh, I have to memorize that? Well, I wouldn't memorize it. I'd think about balloons. Balloons are fun to think about, right? So you've got 3 electron groups. Well, what are 3 balloons going to do? They're going to make this trigonal pattern. It's going to be flat, right? And then ask yourself, well, do I have any lone pairs? If you have a lone pair, then just make one of these invisible. Don't move anything, just make it invisible and describe what's left. So if you have 2 bonding groups and 1 lone pair, this would be bent. There's a lone pair sticking up in the other trigonal planar position. We see 4 electron groups a lot. So 4 electron groups are going to make a tetrahedral shape. So here's that tetrahedron. Methane, classic little tetrahedron molecule. And then ask yourselves, well, how many lone pairs? Well, if I have 1 lone pair, I'm going to erase one of these and I'm going to get this shape. It's a pyramid with a triangle at its base. If I have a second lone pair, I'm going to erase another one of these and then I have a bent structure. Any questions?
The double bonds, they still count as one group.
Double bonds count as one group. Single bonds count as one group. Triple bonds count as one group. Lone pairs count as one group.
This molecule only had two different elements in it. It wouldn't matter what kind of symmetry it had, right? Because
Correct.
it only has 2 and
If you have a diatomic element with just 2 atoms, doesn't matter if it's a single bond, double bond, triple bond, it's going to be linear because 2 points, you can only make a line. With 3 points, you can make a line or you can make a 2-dimensional shape that's a triangle. And with 4 points, then you have more options. So here are the instructions for predicting geometry. You need to start with the correct Lewis structure. Find the total number of electron groups around the central atom. Find the number of bonding groups and the number of lone pairs. And these instructions from your textbook just slay me. Refer to table 10.1 to determine the electron geometry and molecular geometry. Well, that's really not a great idea because I'm not going to give you that table on an exam. So we're not going to do that. Determine the electron and molecular geometries by considering how the electron groups can get as far away from each other as possible. Think balloons. Okay, so let's do an example. Predict the molecular geometry of ClNO. And here it's telling us nitrogen is the central atom. We can't use ideas of symmetry or anything else to figure that out. So we want to put nitrogen in the middle, and we're going to put chlorine and oxygen next to it. So typically we draw these in a line. I'm not sure why. Now we need to count electrons, right? Chlorine has 7 valence electrons. Nitrogen has 5. Oxygen has 6. So what is that? 18, right? Then we put single bonds to connect these. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18. Somebody's going to have to share. How do we decide? Well, you are not equipped to decide who shares. in this question, you are going to come up with the same correct molecular geometry regardless of who shares. This is not a situation where there's resonance in Chem 3A because the chlorine and the oxygen are different. And so it turns out that oxygen's the one that's going to share. You have no way of knowing that. You'll end up with the same answer even if you give the double bond to chlorine. Because what we're concerned about is not who has the double bond, but how many electron groups on the central atom. So we've got octets for everybody now. We look at nitrogen, the central atom. How many electron groups? Not one. Not four. Three. 3 electron groups. So here's nitrogen. 1 electron group. The double bond is another electron group. And the lone pair is an electron group. It has 8 valence electrons in the structure. It has 3 electron groups. So don't go look at the table. Think about balloons or draw a picture and say, well, I've got 3 things that are trying to get away from each other, right? So that's going to make a triangle, right? And here, this one has an atom, this one has an atom, and this one is a lone pair. So the electron geometry would be what? Planar triangular, okay, or trigonal planar. The nice thing about a multiple choice exam is you just have to recognize the correct answer. You don't have to come up with it. So, electron geometry, I'm going to call that EG. The electron geometry is trigonal planar. It's a triangle and it's flat. But this wants molecular geometry. So molecular geometry, we're not going to move anything, but we're going to make that lone pair invisible. It's still there. If you are walking across the runway and you run into Wonder Woman's airplane, you're going to feel it, right? It's solid, it's just invisible. So it's still there. Molecular geometry, we describe what's left after we make lone pairs invisible. What's left? It's bent. So the molecular geometry, trying to write with the eraser, that's not good. Molecular geometry is bent. Any questions? Lewis structure first, electron geometry, then molecular geometry.
Is the 3-dimensional one also bent if it has 2 invisible pairs?
Yes.
Okay.
Yep. So let's do sulfite ion. Now they're not telling us what the central atom is, but here we see there's 1 sulfur and 3 oxygens, so you put the sulfur in the middle and put the oxygens around it. Okay, so sulfur in the middle, and put an oxygen here, an oxygen there. I'm going to choose to put this oxygen on top, doesn't matter. Count electrons. So oxygen and sulfur are both in group 6. So they all have 6 valence electrons. So we've got 3 oxygens and a sulfur with 6 valence electrons. -2 says I have to add 2 because I'm getting a -2 charge because there's 2 extra electrons. So that's 26. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Yes?
What did you distribute to sulfur last because it's most central?
It doesn't really matter how you distribute the electrons. As long as you get the octet. And so if you watch some of the old videos, I kind of do it differently each time, somewhat on purpose, because exactly how you distribute those doesn't matter. And then to finish this off, we would need brackets in the charge. So there's the Lewis structure. That's the first step. Now we ask ourselves, how many electron groups in the central atom? 4 electron groups. So I'm going to draw 4 electron groups. And I'm getting ahead of the lecture notes a little bit, but we use this wedge to indicate that something's coming out of the plane of the screen, and this dashed wedge to indicate that it's behind. So this is jumping out at you, and this is behind. Someone should invent 3D glasses so that we could see this in 3D. So 4 electron groups. The electron geometry is what? 4 is tetrahedral. Molecular geometry, we have to see, well, are there any lone pairs? Yeah, there is. There's one lone pair. So that means I need to make one of these invisible. I'm just going to choose the one on top because that makes what's left easier to look at. And what is the name of that shape?
Triangular pyramid.
Yeah, triangular pyramid or trigonal pyramid. It's not planar because it's not flat. Question?
Yes, I thought the ones when they were by themselves.
Yeah, this is a lone pair right here.
Right. Why'd you take them top?
Well, because you could rotate this around. And I just think this is easier to look at than try to describe the shape of something that's just sort of random. The relationship between this and this, these can rotate in space, and so the fact that this is on the bottom and here I drew the lone pair on the top doesn't matter.
And the long is just that you recognize that the lone pair is a lone pair.
Mm-hmm. You just need to recognize that the lone pair is a lone pair. What I'm trying to help you understand is the process for figuring this out. Whether you actually draw it or you see it in your mind, you take the number of electron groups, 2 is linear, 3 is trigonal planar, 4 is tetrahedral. Imagine what the balloons did, right? It's become a trigonal planar thing now because the pink balloon's dead. Imagine what the balloons do, okay? That's not too hard, right? 3 things to think about. Then make anything that's a lone pair, if there's a lone pair, make one of the balloons invisible and describe what's left. So that's what we're doing. This was tetrahedral. I make one of them invisible because there's a lone pair and then it's trigonal pyramid. Yes?
Also for the electron group, for the CL and L, you wrote that there was, you said there was only 3.
Mm-hmm.
And you said that the bonds equal the electron group.
A double bond is one group.
Right. Oh, and a lone pair is also.
A lone pair is also a group.
Never mind.
Yep.
Well, then wouldn't CL and O before too? Because N had a double bond and also had 3 bonds.
We're looking at the lone pairs on the central atom only. And a triple bond is one group, a double bond is one group, a single bond is one group.
You count them. Okay.
Yeah. So like, you know, my husband and I have this triple bond, right, of 6 children.
Mm-hmm.
So they're part of the family. Now the family, my kids could get away from some other family's kids, but they can't really get away from each other because even if they run away, they're still part of the family. They're stuck with us, if that helps at all. You had a question?
I don't really get how you chose where to put the dashed lines, the straight line, and the wedge, all of that.
It's my habit. So drawing 3-dimensional things on a 2-dimensional surface is challenging, right? And so this is one technique. Another one is, you know, to be more artistic. I'll try.
I guess how do you know when you're supposed to do that? Is it because there are 4 electron groups and you know it's...
There are 4 electron groups, and so I know that that's going to make a tetrahedron. Oops.
though, to draw that three-dimensional representation.
Yeah, I wouldn't do a three-dimensional thing if there were only three groups.
Yeah.
Because three groups just make a triangle. It's flat. Right? So this is three groups. Four groups. When I added the fourth balloon, it pushed the three balloons that were there before closer together. They kind of, and it bumped the center up a little bit.
Okay, why can't one of the other oxygens be a line instead of a dash?
Well, it could be.
Or because it's tetrahedral, four faces, right?
Yeah, it's going to be the same. So let's get rid of this. So I had this with my 4 electron groups. I could choose to make any one of them the invisible one. I can make that one invisible. That's a little harder to recognize just because of how it's drawn as a trigonal pyramid. I could make this one invisible. Again, it's a little hard to recognize that that's a trigonal pyramid.
I thought you could only make lone pairs invisible. It can be any electron group.
What I'm saying is that I drew this picture with 4 groups. One of them has to be invisible. It doesn't matter which one I make invisible. There's 3 oxygens and there's 1 lone pair. So I can make this one the lone pair, and then maybe let's just draw it as a lone pair. These are oxygens, this is a sulfur, and that's my lone pair. It doesn't matter where you put it, because just like with this model, I can rotate it, right? So I can have, if I make that the lone pair, I can put the lone pair up, I can point it towards me, I can point it down. It's just how are you happening to draw it? I prefer to draw them in the same orientation every way, because then you get used to looking at them and it's easier to see what that is supposed to represent. Any other questions? So here's this notation. Straight line means that it's in the plane of the paper. Hashed line means it's going behind the paper or the screen, and the wedge is sticking out at you. And so here's how they represent these. Linear, trigonal, planar, and bent can be drawn very easily because they are two-dimensional. We don't have to draw the lone pairs necessarily. This probably has lone pairs on it, but when we look at molecular geometry, we don't have to draw them. Here's tetrahedral and here's trigonal pyramid. I have a hard time looking at these. These look like just messes to me because I am used to drawing them in the same way all the time. So I would draw it like this. A with an X on the top, and I'd stick this one over. So those are in the plane of the paper, and then this one is sticking out at me, and this one is behind. I always draw it the same way, and so it's easier to look at. This looks like a mess to me. But just be aware that that's what the wedge and the hash means.